Okay, so far we've been kind of very suspiciously only talking about atoms. But since we've been through chapter 5, we'll know a little bit more about all these different kinds of compounds. So, what about those? Well, remember, oftentimes atoms aren't just existing alone, hanging out by themselves in their little solitary land. They're usually involved in some kind of molecule or compound. So we also need a way to think about how to move molecules and compounds from that individual submicroscopic level to that macroscopic level, again, that we deal with like in the lab, for example. Well, it's basically the same idea all over again. So remember, there are 6.022 times 10 to the 23rd of anything in a mole. So why can't it be molecules? Why can't we have 6.022 times 10 to the 23rd molecules in a mole? We sure can. So we're going to work through some examples just to show how this works with molecules, even though it's going to be basically the same thing we were looking at. So we're going to go ahead and work through the first problem here on your screen. So we want to know how many molecules of NO are in 0.345 moles of NO, okay? So if I'm looking at my problem, it looks like I have moles and I want to go to molecules. Okay, so I have moles and I want to go to molecules. So moles to molecules. All right, so again, I do have a relationship that directly links moles to molecules, and that is there are 6.022 times 10 to the 23rd molecules in 1 mole. Okay, so this can get kind of tricky because we're talking about moles and molecules, so you're going to want to make sure that you're fully writing out the word molecule in every case. And remember that if you're choosing to abbreviate mole, it's MOL for the abbreviation. So, okay, so I want to be able to convert from moles to molecules. It looks like I have a direct relationship here to relate those two. So let's go ahead and set up our problem. So it tells me I have 0.345 moles of NO, nitrogen monoxide. So this is nitrogen monoxide. So I have 3.45 moles of nitrogen monoxide. And then from here, I want to be able to convert from moles to number of molecules. So in that case, what I have to be absolutely certain of is I'm making sure that my units cancel out. So if I have moles of NO on top, I want to put that 1 mole down on the bottom. And then I have 6.022 times 10 to the 23rd molecules of NO at the top there. Okay, so I'm going to check my units, see where I'm at. So I have moles of NO at the top, moles of NO at the bottom. Those are going to cancel out, which leaves me with molecules, and that's what I'm looking for. So let's go ahead and math this out in our calculator. And what we end up getting is 2.08 times 10 to the 23rd molecules of NO. Okay, so again, pretty straightforward. All we're doing here is the same kind of problem. Now we're just thinking about, we've just got that number of molecules rather than that number of moles. So let's go ahead and we will work through the second problem here on your screen. So in this case, what we want to know is how many moles of NaCl are in 3.01 times 10 to the 23rd molecules of NaCl. In this case, I am going to see what it's asking me, see where I'm going. All right, so it looks like I have a number of molecules of NaCl, and I'm looking for moles. So we're looking to go from molecules to moles. Okay? Well, I do have a direct relationship between number of molecules and moles. We just used it. It's our best friend, Avogadro's number. So we have 6.022 times 10 to the 23rd molecules and that equals 1 mole of molecules, okay? So we're going to go ahead and use this information as we've written it to solve our problem. So I have 3.01 times 10 to the 23rd molecules of NaCl. And I want to convert that to moles. So that means I want to make sure molecules cancels out. So I'm going to put 6.022 times 10 to the 23rd molecules of NaCl. Sorry, I ran out of room there. Molecules of NaCl, and that's for every 1 mole of NaCl. Okay? So I'm going to check my units, see where I'm at. So therefore, if I have molecules of NaCl on the top, molecules of NaCl on the bottom, they cancel out. I'm left with moles. That's what I'm looking for. We are good to go. So let's math this out and see what we get. If we type all of this into our calculator, we end up with 0.450 moles of NaCl. So when we're just thinking about the mole concept, it's pretty easy here. It's the same idea. How many molecules, how many atoms, how many eggs, how many cats, how many dogs. It doesn't matter what we're thinking about. There are 6.022 times 10 to the 23rd of that thing in a mole. So even if it's molecules, even if it's atoms, even if it's ions, even if it's anything, that's how it's going to work. So we're going to think about also how to translate this to grams and mass in just a second here. Okay, so we've been talking about, molecules and moles. However, again, this kind of isn't very useful. You're not going to go in the lab and get, 0.21 moles of carbon dioxide. We're going to need a more practical way to deal with this, of course. So, again, when we're converting between atoms and elements up to mass, we're going to use the molar mass. However, if we're dealing with a compound rather than just a individual atom, we need to take this into account. We need to take it into consideration. So instead of just using the molar mass, we're actually going to use the formula mass in this equation. Ding, 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 ding. So remember, we did the formula mass a little while back. So if you don't remember how to calculate the formula mass, I highly recommend you go back, you rewatch the videos, you find the chapter that you need to be rereading through and check that out. Our formula mass before was, how much mass does this compound have? And we were thinking about atomic mass units. However, remember, as we talked about with our atoms, on the periodic table, that same number that represents the atomic mass also represents the molar mass. So if we want to know the kind of formula mass of our equation, what we're going to want to do is make sure we're multiplying by the molar masses. So all this does is, again, flip our units from grams to mole from AMU. So in this case, again, we're just looking at our grams per mole rather than atomic mass units. So we can use formula mass to convert between a number of molecules and the mass that those molecules take up. So I've put in a screenshot of the formula mass equation down there. Remember, atomic mass here can just be substituted for molar mass. So it's just saying the number of atoms of the first element times that molar mass, the number of atoms of the second element times that molar mass, number of atoms of the third element times its molar mass, so on and so forth, and then you add all of them up together to get the formula mass, okay? So as we're working through these problems, I'm going to calculate the formula mass on the first problem as a refresher, but after that, I am just going to say, okay, I've calculated the formula mass and use that formula mass because we should have been practicing how to calculate these formula masses a while back. So we're going to go ahead and work through the first problem that you see on your screen right now. So we want to know how many moles are in 12.01 grams of carbon dioxide. So we have 12.01 grams of carbon dioxide, and we want to change that to moles, okay? So we're going to go from grams, which is mass, to moles. Okay, so I'm trying to think about how to relate mass and moles. Well, when I'm thinking about relating mass and moles, I can use some of that information from the periodic table. Before it was the molar mass, and now we're going to have to calculate the formula mass. So I'm going to calculate the formula mass of carbon dioxide because it's going to help me relate the mass of the carbon dioxide to the number of moles I have. So if I want to know the formula mass of carbon dioxide, this is going to be the number of carbon atoms times the molar mass of carbon plus the number of oxygen atoms times the molar mass of those atoms. Okay? So remember, the molar mass is on the periodic table. That's where we're getting it from. So let's go ahead and fill out the formula I have written here. So we want to know our number of carbon atoms in carbon dioxide. Well, carbon has no subscript. We assume that's a subscript of 1. So I have 1 carbon atom. And then when I check out my periodic table and I want to know the mass of carbon, carbon is number 6. So it's in the top row. My molar mass of carbon is 12.01 grams per mole. So that's 12.01 grams for every 1 mole. And to that, I am going to add oxygen. So if I'm looking at the chemical formula carbon dioxide, well, it has 2 oxygen atoms. So I have 2 oxygen atoms times the molar mass of oxygen, which again, I can get from the periodic table. So oxygen is number 8 in that first row, and its molar mass is 16.00 grams per mole. So this is 2 times 16.00 grams for every 1 mole. All right, so if I go ahead and I calculate this out, I end up getting 44.01 grams for every 1 mole, okay? So my formula mass of carbon dioxide, so that I can relate mass to moles, is 44.01 grams for every 1 mole, okay? So now that I have my formula mass, again, I'm trying to go from grams, which is mass, to moles. I have this relationship that 44.01 grams of CO2 equals 1 mole of CO2. So I think I have the information I need here to solve my problem. I'm going to start with my given 12.01 grams of carbon dioxide. And I'm going to use my formula mass here so that I can determine the number of moles that are contained within 12.01 grams of carbon dioxide. So if I have grams on top and I'm trying to cancel that out to get to moles, I'm going to put grams on bottom. So I've got 44.01 grams of carbon dioxide, and I have 1 mole of carbon dioxide on the top, therefore. So 44.01 grams for every 1 mole. I'm going to check my units, see where I'm at. So I've got grams of carbon dioxide on the top, grams of carbon dioxide on the bottom. Cancels out. I'm left with moles of carbon dioxide on the top, and that's where I was headed. So I think I'm on the right track. So I'm going to do my math, multiply this out, and in this case, I have 0.2729 moles of CO2. And remember, we just multiply across and divide down to get there. So multiply across, divide down, and that gives us 0.2729 moles of carbon dioxide. Not too bad. Not too bad. So let's go ahead and work on the next problem as well. So the next problem says, how many grams are in 8.063 moles of N2O, okay? So we want to know how many grams are in 8.063 moles of NO2. So, I'm kind of given moles, and it wants to know how many grams. So I'm trying to go from moles to grams, and again, that's mass is what grams represents, of course. So in this case, you can find my math for how I calculate the formula mass in the slides. However, I'm just going to go ahead and use the formula mass that I have already calculated, which in this case for N2O happens to be 44.02 grams of N2O for every 1 mole of N2O. Okay, so again, if you need a refresher on how to calculate that formula mass, you can see examples of these calculations of the formula mass in the slides, as well as you should go back and review the formula mass videos from earlier in the semester. Okay, so it kind of looks like I have the information I need here. So I have grams, I have a relationship between grams and moles. I have this relationship between grams and moles, and I'm trying to transfer myself between grams and moles. So let's set the math up and see if we have what we think. So we have 8.063 moles of N2O. And I am going to use my formula mass as a conversion factor, so that if I have moles of N2O on the top, I'm going to want to put moles of N2O on the bottom so I can cancel those out and get to grams, my goal. So I'm going to put 1 mole of N2O on the bottom, which is the same as 44.02 grams of N2O. Okay? So let me check my units, see where I'm at. I've got moles of N2O on the top, moles of N2O on the bottom. Those cancel out. So I'm left with grams of N2O, which is what I wanted. So if I go ahead and I complete the math on this problem, I end up with 354.9 grams of N2O. So this is just these are 2 quick examples of how to go between grams and moles. And again, oftentimes that's going to be our main calculation that we need to work through, is between grams and moles. So these are going to be very important. Continue to review them. Make sure you understand them as you work through these problems, okay? I'm going to do another couple of examples here that are going to describe the relationship between molecules and grams, okay? And so now remember, if we want to know, is it kind of like 1 step or 2 steps, we could say, in these problems? Number 1 and number 2 are 1 step because we have a direct relationship between amount of mass and a number of moles. However, number 3 and 4 are asking us to relate molecules in grams. Well, I don't have a relationship between molecules and grams specifically, so I'm likely going to need to use an intermediary, and in this case, it's going to be the mole. So let's go ahead and work through the next problem you see here on your screen. We want to know how many molecules are in 983.56 grams of magnesium hydroxide, MgOH, big parentheses around the OH, 2. So we've got grams, we have 983.56 grams, and we're looking for number of molecules. So we've got grams, which is mass, and we're looking to go to molecules. So again, my big tip off here is that I don't have a direct relationship between grams and molecules, so I'm likely going to need to use an intermediary. And how I determine what I use is, well, I've got a relationship on the periodic table from the formula mass that relates grams and moles. And I know how many molecules are in a mole. So if I convert my number from grams to molecule or grams to moles, I can then go from moles to molecules. So that's the idea here. So let's go ahead and work this problem out. So as I mentioned, we're likely going to need the formula mass. So I've already calculated the formula mass of magnesium hydroxide to be 58.33 grams for every 1 mole of magnesium hydroxide. So again, you can find the math for how I worked this out in the slides. But my formula mass for magnesium hydroxide is 58.33 grams for every 1 mole. Okay? And then I also know that there are 6.022 times 10 to the 23rd molecules in every mole. Okay? So I've got a relationship between grams and moles. I've got a relationship between moles and molecules. I think I can get to the end. Let's see if we're right. So I'm going to start with the information I'm given, which is 983.56 grams of MgOH2. And I'm going to want to get rid of grams right away. So I've got grams on the top, so I'm going to want to use a conversion factor relationship that puts grams on the bottoms. So I'm going to say this is 58.33 grams of magnesium hydroxide for every 1 mole of magnesium hydroxide. Okay? So let me just check my units, see where I am. So I've got grams on the bottom, grams on top. Those are going to cancel out. And I'm left with moles. So I'm left with moles on top as of right now. So I'm going to see what I can do about that. If I have moles on top, I do have this relationship here where I'm relating moles to molecules. Molecules is where I'm going, and I'm in moles. So I'm going to go ahead and use Avogadro's number to figure out how many molecules are in 1 mole. Okay, so now that I've checked my units, I can see that I have moles on top, and I want to be able to cancel out moles. So I'm given the relationship that there are 6.022 times 10 to the 23rd molecules in 1 mole. So in that case, I'm going to use that information to put myself in molecules rather than how this number is currently in moles. So I'm going to put 1 mole of MgOH2 on the bottom. And then I'm going to put 6.022 times 10 to the 23rd molecules of MgOH2 on top. Okay? So if I double check my units again, my grams still cancel out. Grams on top, grams on bottom, canceled. However, now I have moles on top, moles on bottom. Those cancel out, and I'm left with molecules, which is where I was trying to go. So if I go ahead and I finish typing all of this information into my calculator, I'm going to end up with 1.0154 times 10 to the 25 molecules of MgOH2. Oop, we're just at the end of my screen here. MgOH2. So if we want to know how many molecules are in 983.56 grams of magnesium hydroxide, that is 1.0154 times 10 to the 25th molecules. All right. One last example here before we get on to the last topic of the chapter. So let's go ahead and do the last example, which is how many grams are in 8.025 times 10 to the 25th molecules of HF, which is hydrofluoric acid. So we have hydrofluoric acid this time. Don't forget, we have acid naming coming up on the exam too. So, all right, so how many grams are in 8.025 times 10 to the 25th molecules of hydrofluoric acid? So I'm given a certain number of molecules and I want to move to grams, so I'm trying to go from molecules to grams, which again is mass. And remembering again that I do not have a direct relationship between grams and molecules, so I'm going to probably need to use some sort of intermediary. And if we're thinking about molecules and numbers of those, we're counting them using Avogadro's number. So that's probably going to come into play here too. So I have the relationship that there are 6.022 times 10 to the 23rd molecules for every 1 mole. But I can also use the formula mass of hydrofluoric acid to go from moles to grams. So that formula mass is 20.01 grams of HF for every 1 mole of HF. So I have molecules, I'm looking for mass. I have something that relates molecules to moles. I have something that relates moles to mass. I think I'm ready to go. So let's set this up. So if I have 8.025 times 10 to the 25th molecules of HF, the first thing I'm going to want to do is, again, cancel out my molecules. So that means I would have 6.022 on the bottom, so that I've got molecules on top, molecules on bottom. They're going to cancel each other out. So 6.022 times 10 to the 23rd molecules of HF. And for every 6.022 times 10 to the 23rd molecules of HF, we have 1 mole. Okay, so if I'm looking at this and I want to check out where I am, where I still have to go, I've got molecules on top, molecules on bottom. Those are going to cancel out. And currently I am in mole for my unit, but mole is not what I'm looking for. I'm looking for gram. So I need to use that formula mass so I can go between the number of moles that I have to the number of grams. So in this case, I want to make sure that I'm canceling out my moles, so I have moles on top. So I'm going to put the mole from that relationship down on the bottom so I know that they're canceled out. So I have 1 mole of HF on the bottom, and for every 1 mole of HF, I have 20.01 grams of HF. Okay, so for every 1 mole, I have 20.01 grams. And again, you can see how I calculated that formula mass in the slides if need be. So I'm going to triple check my units, see where I'm at. Molecules on top still, molecules on bottom still, cancels out. Moles on top, moles on bottom, those cancel. And I'm left in grams, which is where I want to be. So if I type this in my calculator, remember, multiply across, divide down. Multiply across, divide down. So this gives me 2,667 grams of HF. Okay, so it was a little bit about how we count molecules and compounds by mass. So if you have any questions, please let me know. I've left you with some practice as well. So please work through those. Let me know if you have any questions on those, guys. Okay, so we have one last topic to cover in this chapter, and it's just, again, a bit more of conversion. We just kind of want to know, if I have a molecular compound, molecules and compounds are made up of individual atoms, right? Well, the thing is like we can use the chemical formula to determine how many moles of each element we have in a compound, okay? So in the chemical formula of carbon dioxide, for example, for every 1 mole of carbon dioxide we have, that is actually made up of 1 mole of carbon atoms and 2 moles of oxygen atoms. So in our 1 mole of carbon dioxide, we actually have 3 moles of atoms in there as well. So we have 1 mole of carbon and we have 2 moles of oxygen, okay? So it seems a little counterintuitive. However, remember, we're just saying that in 1 mole of carbon dioxide, that's saying that we have 1 mole that contains all 3 kinds of those atoms in a ratio of 1 carbon atom to 2 oxygen atoms. So this is just making it apparent exactly how many atoms we have overall. So we can use moles to compare, like 6.022 times 10 to the 23rd molecules, but there are still more atoms contained within each of those individual molecules. So each molecule is 1 molecule, but it's made up of 3 atoms, okay? So if we have 1 mole of carbon dioxide, that's made up of 3 atoms. So we're getting a mole of each kind of atoms from there. So 1 mole of carbon, 2 moles of oxygen in that case. So let's work through a couple of examples here on your screen. So if I have 1 mole of silicon dioxide that you see on your screen there, if I want to know how many moles of silicon I have, well, there's 1 silicon atom for every 1 molecule of SiO2. So therefore, if I have 1 mole of SiO2, I have 1 mole of silicon. 1 mole of SiO2 gives me 1 mole of silicon back out from there. So if I want to know how many moles of oxygen are in silicon dioxide, I would have 2 moles of oxygen for every 1 mole of silicon dioxide because I see that subscript of 2 on my oxygen atom, okay? Pretty straightforward when we're dealing with 1 mole. It kind of has to do with the subscripts because the subscripts are telling us how many of each kind of atom make up that molecule. So if I have 1 mole of that molecule, I've got a certain number of atoms beneath that. However, there may be instances where we don't just have 1 round mole of our compound. In this case, we might look at magnesium nitrate on your screen. So on your screen, I have written magnesium nitrate, and I'm asking, how many moles of magnesium are in 3.86 moles of magnesium nitrate? Well, I only have 1 magnesium atom for every mole of magnesium nitrate, so I have 3.86 moles of magnesium in my 3.86 moles of magnesium nitrate. However, I have to be a bit more careful when I'm thinking about the nitrogen because I don't just have 1 mole of nitrogen kind of coming back out of this. I actually have 2 nitrogen atoms in magnesium nitrate. So, if I want to know how many moles of nitrogen are in magnesium nitrate, and I have 3.86 moles of magnesium nitrate, I'm going to need to go ahead and multiply that number by 2 so that I can get 7.72 moles of nitrogen. So if I have 3.86 moles of magnesium nitrate, I have 7.72 moles of just nitrogen contained within there. Okay? And then I also might want to figure out, how many moles of oxygen. Well, it's the same thing. We have to look at how many oxygen atoms we have per magnesium nitrate. In this case, we have 6 oxygen atoms. So if we have 6 oxygen atoms for every magnesium nitrate, and we have 3.86 moles of magnesium nitrate, we're going to want to multiply that by our 6 atoms for every mole or every molecule. So we get 23.2 moles of oxygen in this case. So while I've been trying to explain this and put it into words, what we're really doing is just taking the subscript and multiplying by the number of moles of the total compound. And that's how we can figure out how many moles of each individual atom we have. Okay. So one thing that we might really like to do is figure out how much of one type of atom makes up a specific amount of mass of a compound, right? So again, it isn't very practical to attempt to account a specific number of molecules in the lab. However, it can be useful for us to figure this out. So let's think about dissolving salt in water, for example, our classic table salt, NaCl. So maybe in my reaction, for some reason, I'm really concerned about the number of sodium atoms I have. Well, I may want to know how many grams of that I get back out in the end. So this is kind of what we're working with. So the idea is we can use information from the formula mass, the molar mass, so we can go between grams and moles and move through our compound, okay? So let's go ahead and work through the two problems you see on your screen, and let's do some examples. Okay, so let's go ahead and work through some examples of how to convert between mass of a compound to mass of an element, okay? So the kind of tricky piece here is that we can't really just compare grams and grams directly, right? We have nothing that says grams of HCl equals so many grams of chlorine. However, we do have some intermediaries. We have some places we can go in the middle, and one of those places is the mole. So we'll talk about this a little bit more when we get to talking about Chapter 8. However, we can't really just directly compare something's mass to something else's mass because, you know, like one carbon atom weighs a lot different than one chlorine atom. One chlorine atom is 35.45 AMU, whereas one carbon atom is 12.01 AMU. So I have two kind of very different things there. Even though I have one atom in each case, I have a very different amount of mass. I have almost 3 times the mass in one chlorine atom versus one carbon atom. So so this is why we cannot compare these directly, is because even if we're just saying I have one atom of each, that doesn't really mean anything to me because I have much different masses. However, this is one of the things that the mole takes care of for us. So it kind of happens in the background that this is what the mole takes care of. Well, I can compare moles of one thing to moles of another because this is just an arbitrary amount that we've decided on, right? So we've said that there are 6.022 times 10 to the 23rd atoms in a mole. So we're not directly comparing mass, we're just comparing a total number of atoms to a total number of atoms. And then we have information later on with the formula mass and the molar mass that we can use to kind of run those comparisons. So we're going to go ahead and do the two problems you see on your screen, and I've left you with some practice at the end as well. So the first thing we want to know is how many grams of Cl are in 25.00 grams of HCl. So how many grams of chlorine are in 25 grams of hydrochloric acid? So I have 25 grams of HCl, and I want to know how many grams of Cl. So I'm going from grams mass of a compound, HCl, to grams mass of an atom that makes up that compound, chlorine, okay? So I have 25.00 grams of chlorine. Well, I know I cannot directly compare grams of chlorine to grams of HCl because this doesn't make sense. So I am going to need to convert to moles in the middle. So I know that I have a relationship for hydrochloric acid between the number of moles and the number of grams of hydrochloric acid. So that's the formula mass. So the formula mass of HCl is 36.46 grams of HCl. And that's equal to 1 mole of HCl. Okay, and then I also know that I cannot just use my grams of chlorine. I'm going to have to at some point convert between grams of chlorine and moles of chlorine. So I'm going to need that molar mass of chlorine as well, which is 35.45 grams of chlorine for every 1 mole of chlorine, okay? So I've got these two pieces of information. However, there's one more piece of information here hidden in your problem, okay? So if I have the chemical formula HCl, so this kind of tells me a couple of things. It tells me that for every 1 hydrogen atom I have 1 chlorine atom, And that's the same thing in ratio as having one HCl molecule. So I have a ratio that compares the moles of each to each other. Remember, I can say that if I have 1 mole of hydrochloric acid within 1 mole of hydrochloric acid, there is 1 mole of Cl. So we're going to leverage this fact again. We talked about it a little bit before. We did a little bit of practice on the screen, but we're going to use this piece of information. I'm just trying to make it more apparent what we are going to use. So let's work through this. So if I have 25.00 grams of HCl, I'm going to want to convert that to moles first and foremost because grams is useless to me of a compound. Moles is everything. So if I have grams of HCl on the top, I'm going to want to put grams of HCl on the bottom, so that I can get those to cancel out, and that's for every 1 mole of HCl. Okay? Now I'm going to need some sort of comparison so I can go from HCl to just Cl by itself. And this is my claim of where we should be using our formula, or our chemical formula. So this is how we use the chemical formula as a conversion factor. So if I have 1 mole of HCl, for every 1 mole of HCl I have 1 mole of chlorine. So I'm comparing the total chemical formula to the subscript of 1 of those atoms within that chemical formula. Okay? So now let me kind of see where I am. I should have stopped sooner and checked my units, but let's check ourselves before we wreck ourselves. So we have grams of hydrochloric acid, grams of hydrochloric acid. As you may have noticed this whole time, I have been making sure I have been writing grams of what kind of compound or grams of what kind of atom I have, and this is why. Because when I'm canceling things out, a unit and an atom or molecule are now tied together. So if I have grams of hydrochloric acid, that can only cancel with grams of hydrochloric acid. It can't cancel with grams of chlorine. It can't cancel with grams of hydrogen. It can't cancel with grams of nitrogen or, I don't know, ruthenium. I have no idea. So I can only cancel grams of hydrochloric acid with grams of hydrochloric acid. So if I have 1 mole of hydrochloric acid, again, I can only cancel that with hydrochloric acid. So in this case, I am left with moles of Cl at this point. However, that's not where we're going. We want to go to grams of chlorine. So I do have that molar mass from the periodic table that allows me to make this relationship. So I have 1 mole of Cl. I'm choosing to put that on the bottom so it cancels out, and that's 35.45 grams for every 1 mole of chlorine. Okay, let's triple check our units. Grams of hydrochloric acid, grams of hydrochloric acid, moles of hydrochloric acid, moles of hydrochloric acid, moles of chlorine, moles of chlorine. We're left with grams of chlorine. That's where we want to be. That's where we're going. If I go ahead and I multiply this out in my calculator, I get 24.31 grams of chlorine. Okay? So, one thing that's interesting here, and one way you can check your answer, is that if I'm multiplying this out and I have a total mass of a compound and it's made up of hydrogen and it's made up of chlorine, my amount of chlorine and my amount of hydrogen should be less than that of the total mass of the compound, right? I'm getting some of my total mass of the compound from the chlorine and some of my total mass of the compound from the hydrogen atoms. So I should have less mass of chlorine and less mass of hydrogen than I do of total hydrochloric acid in my compound. So if I started with 25 grams of hydrochloric acid, it's a pretty good sign that my grams of chlorine is smaller than that, okay? So if you end up with a larger number of one kind of element within your compound, you end up with a mass that's way bigger, something's wrong. Go back through, double check what you've done. So otherwise, this one looks like it's right on track. And hypothetically, if we also solved the same problem for how many grams of hydrogen we have, we should have actually two masses that add up to 25.00 approximately then. So if I have my mass of chlorine and my mass of hydrogen, if I add those up, I should have my total mass of hydrochloric acid. So in this case, I have 20.31 grams of chlorine. If I figured that out, or if I figured out the mass of hydrogen in this compound and I added them up, I should get that total mass of HCl in that case. So just some forewarnings, some ways to check your answers. All right, let's go ahead and do the last problem here, and then I will leave you to work the practice ones by yourself. So we want to know how many grams of sodium are in 32.45 grams of NaOH. Okay, so I have 32.45 grams of NaOH, and I want to know how many grams of sodium. So I'm going from grams, which is mass, of NaOH, and I want to go to just grams or mass of sodium, okay? So we're going to work through the same process here. We're going to need the formula mass, we're going to need the molar mass, we're going to need the chemical formula, and I think that'll do it. So the formula mass of NaOH is 40 grams of NaOH for every 1 mole of NaOH. Okay, so 40 grams for every 1 mole of NaOH. And then if I check out sodium on the periodic table, sodium's formula mass is 22.99 grams of sodium for every 1 mole of sodium. Okay, so let's go ahead, let's set this problem up and see if we can't get where we're going. So I have 32.45 grams of NaOH. I know I want to transfer that into moles so that I can compare it to the moles of sodium I would have so that I can use that information to get to the grams. So I'm first going to convert to moles. So if I have grams of sodium hydroxide on the top, I'm going to want to put grams of sodium hydroxide on the bottom so that I can cancel that unit out. So I would have 40 grams of NaOH for every 1 mole of NaOH. So let's check our units. So now it looks like I've got grams of NaOH on the top, grams of NaOH on the bottom. Checks out. We're left with moles of NaOH. So if I'm at moles of NaOH, I can compare the moles of sodium to the moles of sodium hydroxide so that I can eventually calculate the number of grams of sodium I have. So if I'm looking at my chemical formula, NaOH, for every 1 mole of sodium hydroxide I have, so for every 1 mole of sodium hydroxide I have 1 mole of sodium because there is no subscript on sodium. So for every 1 mole of NaOH, okay, so I've got 1 mole of NaOH on the bottom. Let's go ahead and we need to figure out how many moles of Na are in 1 mole of NaOH. Well, again, that comes from my subscript, so I'm going to put 1 mole of Na on the top and see where that's gotten me. So let's triple check our units again and see what we got going on. So grams of sodium hydroxide on the top, grams of sodium hydroxide on the bottom, those cancel out. Moles of sodium hydroxide on the top, moles of sodium hydroxide on the bottom, those cancel out. We are now in terms of just sodium atoms, okay? So we've got 1 mole of sodium atoms. However, our problem is asking us to go all the way to the mass of those sodium atoms. So while moles is interesting, it's not our end point for this problem. So I do have that molar mass that relates the number of grams to the number of moles of a compound. So therefore, I'm going to put 1 mole of sodium on the bottom so that my moles of sodium can cancel out, and I'm going to be left with 22.99 grams of sodium on the top. So let's triple check our units one more time, make sure we got where we're going. So I have grams of sodium hydroxide on the top, grams of sodium hydroxide on the bottom, cancel out. Moles of NaOH on the top, moles of NaOH on the bottom, canceled. Moles of Na on the top, moles of Na on the bottom, canceled out. We're left with grams of sodium, and that's what we're looking for. So if I type this in my calculator, I again multiply across, divide down, we are left with 18.65 grams of sodium atoms, okay? So again, remember, we're trying to go from the number of grams of an amount, the amount of grams of a compound, and we want to figure out the mass of one of those elements making it up. So I'm checking my answer. 18.65 is lower than 32.45. I think that makes sense to me. So what I want you guys to do is make sure you work through these practice problems and see if you can't try some of these out. And that is our content for Chapter 6. So please, please, please just let me know if you have any questions. And Bob's your uncle.